and when the sun returns to its starting point, a sidereal year has passed. This motion is difficult to observe directly because the stars cannot be seen when the sun is in the sky. However, if you look at the sky before each dawn, the annual motion is very noticeable. The last stars seen to rise are not always the same, and within a week or two, an upward shift can be noted. As an example, in July in the northern hemisphere, Orion cannot be seen in the dawn sky, but in August it becomes easily visible. Measuring a year this way gives a period that is 365 days, 6 hours, 9 minutes, and 10 seconds long. Another possibility is to measure the year against the passing of the seasons. Because of the tilt of the Earth on its axis, the position of the sun in the sky changes from day to day throughout the year. If we were to take a picture of the sun at noon regularly throughout the year, we would see the sun moving on this path called an analemma. On the days in its orbit when the Earth is at a maximum tilt towards or away from the sun, the length of the daylight is at a maximum or a minimum. These days are called solstices, and the sun will be at the top left or bottom right of the analemma. On the days when the Earth's tilt is perfectly sideways to the sun, the day and night are equal in length. These are the equinoxes, and the sun will be at this crossover position in the analemma. When the sun goes from one vernal equinox to the next, a tropical year has passed. Measuring this way gives a year that is 365 days, 5 hours, 48 minutes, and 46 seconds long. The length of a year on Earth is affected by several gradual and cyclical changes in its orbit and its tilt. First, there is the precession of the Earth's axis. Over a period of about 26,000 years, the Earth's axis traces out a circle in the sky. One result of this is that the North Star changes over time. Right now, the Earth's axis points towards Polaris. 5,000 years ago, the axis pointed to a star in the constellation Draco. And 12,000 years ago, the brilliant star Vega was the pole star. And because of the 26,000-year cycle, Vega will be the pole star again in 14,000 years. The precession of the equinoxes is caused primarily by gravitational forces of the sun and the moon acting on the Earth. While the axial tilt is the primary cause of seasons on the Earth, the distance from the sun, which changes throughout the year because of the elliptical shape of the Earth's orbit, contributes a small bit of temperature variations throughout the year as well. When the axis is aligned so it points towards the sun during perihelion, one hemisphere will have a greater difference between the seasons, while the other hemisphere will have milder seasons. The hemisphere, which is in summer at perihelion, will receive much of the corresponding increase in solar radiation. But that same hemisphere will be in winter at aphelion and have a colder winter. The other hemisphere will have a relatively warmer winter and cooler summer. When the Earth's axis is aligned such that aphelion and perihelion occur near the equinoxes, the northern and southern hemisphere will have similar contrast in the seasons. At present, perihelion occurs during the southern hemisphere's summer, and aphelion is reached during the southern winter. So the southern hemisphere seasons are somewhat more extreme than the northern hemisphere seasons when other factors are equal. In addition, the gravitational effects of other planets cause the ellipse of our orbit to slowly spin around the sun. it takes about 112,000 years for the ellipse to revolve once, relative to fixed stars. When considered together, the two forms of precession add, and it takes about 21,000 years for the solstice to go from aphelion to aphelion. The dates of the perihelion and the aphelion advance each year on this cycle, an average of 1 day per 58 years. The eccentricity of the Earth's orbit is a measure of how round or how oval the orbit shape is. Over thousands of years, the eccentricity of the Earth's orbit varies as a result of gravitational attractions among the planets, primarily Jupiter and Saturn. The orbital eccentricity cycles with a period of roughly 100,000 years. As the eccentricity of the orbit evolves, the semi-major axis of the orbital ellipse remains unchanged, so the length of the sidereal year remains unchanged. As the Earth travels in its orbit, the duration of seasons depends on the eccentricity of the orbit. When the orbital eccentricity is extreme, the seasons that occur on the far side of the orbit are substantially longer in duration. In addition to axial precession, there's the axial tilt, the angle the Earth's rotational axis makes with its orbital plane. It is currently about 23.4 degrees and is declining. This tilt varies from 22.1 degrees to 24.5 degrees. It makes one complete tilt and back every 41,000 years. This change in tilt is directly related to ice ages on Earth. The last maximum tilt occurred in 8700 BC, and the next minimum tilt will happen in 11,800 AD. The inclination of Earth's orbit drifts up and down relative to the present orbit, with the cycle having a period of about 70,000 years. And the orbit also moves relative to the orbits of other planets as well. By calculating the plane of unchanged total angular momentum of the solar system, we can define the orbital plane called the invariable plane. It is approximately the orbital plane of Jupiter. The inclination of the Earth's orbit has a 100,000-year cycle relative to the invariable plane. This 100,000-year cycle closely matches the 100,000-year pattern of ice ages. A year on Earth is directly determined by all the various orbital motions of the Earth. So, if someone tells you how many years old they are, you might ask them, is that sidereal, tropical, or anomalous years?